Welcome to the third live Anyscale Academy. Today we're going to talk about Ray Tune and Ray Serve. This will be about 2 hours. We'll record this and also make the information available later. If you want to find out more information about Anyscale events this year, including past events, the videos for them, and so forth, check out anyscale.com/events. Let me get the right window here. There we go. We're happy to announce that we're going to have Ray Summit September 30th and October 1st. There'll actually be a tutorial day on the 29th as well. This is free. It's online. We really encourage you to register. You can either go to raysummit.org or anyscale.com/events to see more information. We've got a really great lineup of keynote speakers, some luminaries in the industry, and we're actually going to add a few more in the next week or so as we're finalizing details. And the schedule is starting to shape up too. So I hope you'll check this out. We're really excited about this event, again, September 30th to October 1st. Some of you may know we've been doing these summer events called Ray Summit Connect, which are 1-hour events every month. The next one will be on the topic of ML ops, using Ray in the real world, and that'll be August 12th. Again, anyscale.com/events is where you can find out more information about that. Now, if you are paying attention, you may have noticed in the tutorial description that we said we'd cover the cluster launcher, formerly known as the autoscaler as well. I decided to pull that out and not do it for the reasons that this is actually undergoing a lot of redesign at the moment, and it's not quite ready. It'll be in the next release of Ray, so I decided to just wait on that. So apologies. I will point out as we get started in the tutorial where you can actually go see information about what's going on right now, and if you're interested in what's coming. Okay, so if you have issues or questions, feel free to post them at any time in the Q&A feature of Zoom, and we'll try to answer them as we go. If you're having problems with your session, you can't get it to work, or you never got the email, post information there as well. You can actually maybe to get session details, we'll send you an email. So go ahead and send an email to academy@anyscale.com. I put this in the chat window as well. And that way my team can send you the details for connecting to a session. But in general, if you have problems with your session, use the name that was in that email to tell us which one is acting up. We actually have some backups if we need to hand them out. But in general, if you have questions about the material, I'll try to answer them as I go. I have the Q&A window open, so just fire away as needed. So anyway, the email should have contained this core bit, which has the session name, and it has these 3 links. One is to Jupyter Lab. That's mostly where we'll spend our time today. There's also the Ray dashboard, which is a monitoring tool for watching what's going on. We'll take a look at that a few times, but not really dwell on it. And then we'll actually look at TensorBoard a little bit when we're doing model training, which we'll use Ray Tune to do. So you might try those links right now in your environment, make sure they work, and then you'll be good to go for the rest of the event. Also, I'll keep these sessions running until about 3 p.m. Pacific time today or so. So if you want to keep playing with the material, you want to download the notebooks that you've edited or whatever, then feel free to do that. But about that time, we'll take everything down because it obviously gets expensive if we run it for too long. Also, I'll point out that we have a couple of surveys, one for the Serve material, one for the Tune material. I'd really appreciate it if you'd fill out those surveys today so that you can give us feedback about what you liked, what you didn't, what you'd like to see, and that sort of thing. I'll show you where those are in the overview notebooks in just a moment. And in general, if you have any feedback, suggestions, stuff you'd like us to cover, whatever, feel free to email us at academy@anyscale.com. If you want to tweet about the event today, you could use this hashtag Anyscale Academy. You could mention the Ray Distributed or Anyscale Compute addresses as well. Once again, I will post the video for this event, and you can actually get all the code now if you want. Just go to this GitHub repo, which is public, our Anyscale account /academy, and you can download everything, including all the materials that we covered in previous tutorials. And this slide I'll put up when we actually take a break in a little bit. So let's get started. If you click your Jupyter Lab link, you should see something like this. There's a ton of Conda environments in this particular Amazon AMI. You don't need to worry about that. Although I will mention what could be useful is this terminal window. occasionally it's useful to bring that up for various purposes. You won't actually need it today, but if you wanted to look at the environment, that's what you would use. Let me start with just a quick overview of the landscape here. This is the whole Git repo. There's courses on advanced Ray. Ray Cluster Launcher is the placeholder I mentioned. Let me actually open that one just quickly. So this is a placeholder, but if you're interested in following along with what's happening, what will be coming in Ray Cluster Launcher, look at this documentation link, which is actually like the bleeding edge version of the docs, the pre-release version. So if you're interested in what's coming, take a look at that. That's all I'll say about this one. Yeah, I'll save it. Here we go. We go back to this. There's also the Ray crash course. Go here if you're new to Ray and you'd like to get the basics of how Ray works. Ray project is actually an implementation detail. The big one we covered last time was Ray RLlib for reinforcement learning. Last time is in last month. Today, again, we'll talk about Ray serve and Ray tune. And there's also a notebook in this reference folder with a bunch of links for other places to go for more tutorials, papers on various topics, and so forth. And the rest of the directories are also support tools. This overview notebook provides an overview for all of the training materials. Basically like an outline of what each of them provides. There's also a section here that discusses which tutorials you might want to look at for various interests and so forth. Once again, we'll be focusing on tune and serve, which are down here. And here's the link to the survey. This is also in the overview notebook for tune itself, which I'll bring up in a second. But I'd really appreciate it if before you finish today, you click that link and fill out that survey. And similarly, there's one here for serve. And the reason there are two surveys is because each of them asks specific questions about the particular notebooks in each one. So rather than one big survey, there's several of them. Okay, so let's actually open up this Ray serve folder and then click on this Ray serve overview. And this, sorry, actually, that's a mistake. I meant to go to the tune one first. So open this one for tune. You can, I'll just close this now, but you can leave it open if you want. Let's close the overview. So, I'm sort of have the window open kind of, or the font kind of expanded here so that it's a little easier to read. You can do what you like on your laptop. All right, so what this tells you is kind of briefly what each of the lessons or notebooks are all about in this tutorial. We'll start with just a brief explanation of what hyperparameter tuning is all about. And many of you may already know about hyperparameter tuning. We won't spend a lot of time with the explanation, but it'll be level setting for everyone who might be new to it. And then basically this notebook and the next two will progressively disclose details about using the Tune API, look at more sophisticated examples as we go so that you can see how you might tweak and work with Tune yourself for hyperparameter tuning. And there's also a final lesson on a new library that eventually may have its own tutorial called Ray SGD, which is a tool for making it easier to distribute training as opposed to hyperparameter tuning, but training of PyTorch and TensorFlow models over a cluster. We'll talk briefly about how that works in this lesson. And then after that, we'll go into serve. Once again, the link to the survey is here at the bottom. If you wouldn't mind filling out at the end, I'd appreciate it. Now you can either click this lesson one here, or you could click, double click over here in the browser on the left. This is probably just slightly easier, one click, and now we're in the first lesson. Okay, so let me go through this a bit. Now I have to say just briefly about the structure of these lessons. They are designed for people to actually do this on their own time. So they tend to be a little on the wordy side as opposed to terseness, because I don't assume that you actually have me talking when we go through this. So you can read this stuff if you want, or you can just listen to me describe things and then evaluate the cells for the code. Now, if you are new to notebooks, if you've never used them before, they're a pretty nice way of interleaving code and comments and graphics and all that sort of thing, which is why we use it. But the way you navigate here is for any cell, and this happens to be a cell I've selected. If I double click this, it turns out this is a markdown cell, and so I could actually edit the content if I wanted to. And then when I hit Shift Return, it'll actually evaluate that cell. Similarly, you could also do this button up here, this run button. It will just run one cell and advance to the next. And that's what we'll do today. I never use the button. I always just use shift return because it's the easiest thing to use. But it will let you walk through the material. When we actually get to code, it will actually run it. Graphs, it will actually graph them, things like that. All right, let me briefly describe what hyperparameter tuning is all about. And you might also look at the references that are in this. Where is this one? Actually, it's the last notebook. References hyperparameter tuning is what this is pointing to. It has a little bit more information. The tune documentation also has some information about hyperparameter tuning in general, as well as, here's a link to the actual API information if you want. I'd also like to recommend that you check out the recent Ray Summit Connect talk by Richard Lau, the main engineer behind Tune, where he lays out the landscape of hyperparameter tuning and what it's intended to do, and talks about some of the features of Tune as well. So this link will take you to information about that event. All right, so what's the idea with hyperparameters? What do we mean? Well, let me just take the simplest example I could think of. Many of you, if you've done any data science, may be familiar with the idea of k-means clustering. It's the idea that I have this data set. It's an unsupervised method, meaning I don't have labels for things, but I suspect that the data clumps in some way. For some set of features, they're actually clumps that might be indicative of classifying what those points are. In this case, this data set happens to be a popular data set about 3 different iris species and the data about them. And the idea with k-means clustering is that we decide either by visually seeing what we have in 2 or 3 dimensions or guessing if it's more than 3 dimensions, how many clusters we think we have. And then there's this algorithm that you run that I won't describe here that tries to find all 3 clusters, and if k is 3, and the centroids, the central location of each one, and then assign each of the data points to one of those clusters. And this nice little animated GIF is illustrating kind of how the algorithm works. It's an iterative algorithm. It eventually reaches a point where it doesn't move anymore, and that's when you know it's done. The interesting thing about k-means for our purposes is that this k is a hyperparameter. It's something you decide ahead of time, and then you run the so-called training algorithm on that decision. And you may not know what k is. In this case, we can see that it's 2 or 3 rather is a good number. You might even argue that 2 would work. But for larger data sets and larger dimensions, it may not be obvious. So you may need a process of finding k, the hyperparameter, before you find the parameters, which in this case would be the locations of the centroids and the assignment of each data point to those centroids. Now, this is not really a very sophisticated problem. You could easily do this brute force, and in this case for k-means, you would probably guess that the best k is the one where the distances to centroids are minimized over the whole data set. For example, if I pick k equals 1, some of the points on the upper left, upper right would be pretty far from the center that it computes, whereas with k equals 3, all the points are closer to a center. So that's sort of one way you could try to do k-means as a hyperparameter problem. Where it really got to be a problem that we had to solve in more sophisticated ways when we started building neural networks. Every single number you see here, actually everything in black in this picture is a hyperparameter. How many layers do we have? What kind of layers are they? Are they max pooling? Are they convolutional? Whatever. All these numbers about sizes, about the sizes of convolutions, whether it's fully connected, dense, or not. All of these are hyperparameter decisions you need to make for your problem before you actually train the model for real on data. So you need to figure out the structure first. In fact, the term in the neural network world is a neural architecture search, or NAS is the term of art for this problem. And it's a big problem because the space of all possible neural networks is enormous. So obviously you can't naively search all possible neural networks to find one that works for you, because it would be computationally ridiculous to try that. So a lot of the art and science of hyperparameter optimization, or hyperparameter tuning, HBO for short, is finding a way, in the most efficient way, finding a good enough solution, a good enough set of hyperparameters like this architecture, before you then find the parameters, which in this case would be all of the weights for each of the cells in each of these layers. So that's a big challenge for us. That's why hyperparameter tuning is so important as a general research problem and as a practical problem. It's really driven largely by neural networks. And Tune is really designed for neural network search, although it's actually flexible enough that you could do other things like k-mean search if you really wanted to. Okay, hopefully that's give you a sense of what hyperparameter tuning is all about if you hadn't really encountered it before. What I'd like to talk about next then is just start introducing you to Tune, and we'll actually do this with some real problems. So RayTune is one of the larger libraries built on top of Ray that exploits the parallelism that Ray gives us over a cluster. And it's designed to make it really easy to do experiments where you do hyperparameter optimization without having to worry about all the challenges of distributed computing. It's basically an extensible, pluggable framework. It does have some built-in specific capabilities, but mostly it integrates with third-party tools that you might want to use. You know, like OpenAI gym environments, which are popular in reinforcement learning, neural network libraries like PyTorch, TensorFlow, scikit-learn, lots of third-party algorithms for so-called search and scheduling, which we'll get to in I think it's the third lesson. I'll explain what those are all about. What Tune is great at is letting you declaratively say how you want all these things to be glued together, and then it just kind of does the work for you. So that's the idea. All right, so let's actually do this. Once again, Shift Enter, and then we'll import Ray, and we'll also import Tune from Ray. So that should have worked fine. Now the next two lines, this one runs a shell script to make sure that Ray is already running. Everyone should see what you're seeing here. Info, Ray is already running. If you don't, something's wrong with your environment. We might need to give you a new session. I'm trying to get rid of this actually, but the reason the shell script is here is to make it easy to both run this in our environment that we're using today as well as on your own laptops when you check out the Git repo. We have, I think, a better solution for this, but it's kind of background information. What's actually going on is we're running a Ray cluster behind the scenes. It's actually a one-node cluster, so it's not that fancy. And what we're going to do with the next line when we say Ray init address equals auto is that it will search for a Ray cluster running and then connect to it rather than start one itself. So that's the idea here. Once again, I'm using Shift Return to navigate, to evaluate the cells and navigate to the next one. And when you ran that line, you should have seen something like this that printed all kinds of information about our object store. You know, the Raylet is like the local daemon process and so forth. Now this web URL, this is actually the dashboard for Ray. If you open that dashboard link I sent you, it'll look something like this. There isn't a whole lot going on at the moment. We haven't actually started running anything in the background. The dashboard's pretty cool. It lets you see globally what's going on in your environment, you know, all CPU utilization and so forth. And when we're actually running Ray tasks, we'll be able to see what they're doing on an individual basis. And we have 4 of these worker processes running right now. The logical view lets you do things like look at actors that are running. If you're familiar with that idea in Ray, you can examine memory utilization and so forth. So there's a lot of cool features, and there's even some visualization of Tune. Okay, let's go back to the notebook. Now, if you went through our RLib tutorial last week, you might recall that we had a simple example of a so-called multi-arm bandit. And we actually used Tune to train it. We're going to play with that a little bit. If you're not familiar with it, then what I encourage you to do is to click through some of the links I've got here. You can do it now if you want, or maybe do it later. Basically, the idea with a multi-arm bandit is it's sort of inspired by the slot machines and casinos, which are one-arm bandits. And they're called bandits because you almost always lose. And a multi-arm bandit would be like a multi-arm slot machine. And it turns out it's a very interesting problem as a way of modeling a lot of real-world phenomena. And this section of the RLib tutorial goes into a lot of details here. What we're going to do is actually use that with a popular environment called Cartpole. And what I will do is just quickly open this up so you can see what Cartpole is all about. It's really a simple model for experimenting with reinforcement learning where I have a cart that moves back and forth in one dimension, and a pole that's balancing on it. And what I have to do is train the cart to move appropriately so that the pole stays balanced. That's the idea with cart pole. So we're just going to use that. And with this one cell, we're going to tell Tune how to find the optimal neural network for this. So let me walk through what's going to happen here. We're going to call tune.run. We're going to use an algorithm in reinforcement learning called proximal policy optimization. Again, it was covered in the RLib tutorial. It's basically just a way of training this system to find the best way of moving the cart, given the current position and whether it's falling or not for the pole, to adjust the cart horizontally, to keep it balanced. We put in a stopping criteria so it doesn't keep running forever or for a very long time. And what we're going to say is that it's good enough if we get to 400 points, where reward mean is, on average, when you run with this particular trained system, you should get about 400 points out of a total of 500 is the maximum. And that when we get to that point, we'll say that's good enough. And then we can pass a configuration object where we tell it that we're going to use this OpenAI gym environment for cart pole version 1. We don't have any GPUs. We'll use 3 num workers. This number is somewhat arbitrary. I picked it because that seemed to work best in these tutorial environments that we're using. But this is the number you could actually leave out, and it would just find a good number for you. And then the key thing is this section where we're actually, as part of our configuration, going to train a very simple neural network, a so-called 2-layer fully connected neural network, or 2 hidden layers. And ideally what we would do is maybe train from very small sizes up to large sizes, but to make this run reasonably fast, and it'll still take about 5 minutes to run. In fact, let's go ahead and do this. Go ahead and evaluate this cell while I talk, because it is going to take about 5 minutes to run. But what we're going to let Tune do is look at all 4 combinations of each network size. For the first layer, it can either be 20 or 40 weights. The second one can also either be 20 or 40. So there's 2 to the 2 combinations there, and Tune will evaluate all 4 combinations and find the best one that works. And one of the things we're going to see when we do this is that we get kind of ambiguous results. It turns out that all of the results will be pretty good, but some of them will train faster than others. So it will come down to thinking about, okay, well, I could take the best score, the one that seemed to return the best results, but maybe actually another choice is good enough and gives me faster training times, which I might want if I train this thing later on over and over again. I'm going to take this set of hyperparameters that I've just created, the size of these neural network layers, and then I'm going to train cart pole over and over and over again. Maybe I want to optimize speed in that scenario, and I'm willing to tolerate a little loss in accuracy or performance. So that's one of the things we'll get into a little bit as we look at the data. Something else that I put in here, well, it's just this other flag. Eager false is a flag for TensorFlow, which is what we're using behind the scenes to tell it not to use eager evaluation. And also, we said verbose equals 1, which means that we'll get reasonably quiet output. This line here, this cell will update as it runs each of these. And you can see that it's going to do 1 at a time, and it'll take a little bit of time for each of these to train. So this is going to run for a bit. And what I would like to suggest you do, you can see that it's now going to the next one. Let's go ahead and take 5 minutes. If you want to take if you didn't get your coffee or whatever, or if you're having any issues, let's go ahead and deal with those now. But we'll just wait for this to finish. And then I have 26 minutes after the hour. Let's start again at 30 minutes after the hour, which is about 4 minutes. And by then, it's probably going to be done. So we'll just take a little break here. There's a question coming up, and I'll go ahead and answer that while it's happening, but don't worry if you want to step away for a moment. So someone asked for clarification about what we're actually doing. And in particular, is this doing like image recognition that maybe you've seen? Actually, it isn't. It's it turns out if you look at those other notebooks from the RLib tutorial, you'll see in more detail what's actually happening in this cart pole environment. There are basically 4 numbers that represent the state of the world, and they are what's the position of the pole along the axis? There's one axis. Is the cart moving one way or the other with a certain velocity? What's the angle of the pole where 0 would be balanced and a negative with falling one way, positive falling the other? And what's the angular velocity? How fast is it falling? So we actually don't have to do any image processing. That image I showed you here is just a visualization that you can see when it's running, so that you get to see how it looks when it's actually working. It's a nice way to see what's happening. I think at the bottom of this notebook, if you're interested, if I remember correctly, there's actually a short video of one of the things running. Unfortunately, in this cloud environment, we can't show it running in real time, but I have a video so you can see what it looks like when you run it. But no, we don't have to do anything with the image of the cart, although you could actually do that. That's obviously been a very successful tool for like training game players, such as the Atari games. In this case, it's a physical problem, and we could actually model the physics exactly, because you can model those physics if you ignore friction and so forth. But what we'll do is just take those 4 numbers I mentioned, and using those as the current state of the world, keep training this policy, as it's called, in this case encapsulated in this network model policy, to come up with a neural network that's smart enough to know what to change in the velocity when the pole is going one way or the other, so that it can actually keep it balanced. And we'll see a little bit more about how that works in a second. How are we doing? We're on the last run. It might be done just right about the time that I said we would start again. It's very close to finished. One thing to notice is the total time and the iterations here. That gives you a sense of some of the stuff we'll talk about in a minute, trading off that kind of performance criterion versus the score. And it's done. Okay. All right, I'll wait just a few more seconds in case people actually took me up on my suggestion to go get coffee, or coffee's probably too much to get in 4 minutes, but maybe water or something. All right, it's the, again, I use verbose equals 1, so we just saw the sort of running status update. If you set this to 2, you get a whole lot of information. In fact, if you want to try this later, I suggest you do that. It's a little much to process because there's so much coming out. By the way, the reason it's scrolling like it is because of this feature that I'll mention in notebooks. If you right-click, you can enable or disable scrolling for outputs. I have it enabled right now for this one, which is why it says scrolling. If you get a lot of output coming out, just turn this on and it won't like overwhelm the notebook. But if you want to see it all, unscrolled, you could do disable scrolling. So we can eyeball some information here. Now, unfortunately, there's a slight bug here where it's not showing those parameters that were used for each of these 4 cases, but we'll be able to see that in just a second. So let's actually look at how we can analyze the results using the analysis object that was returned by Tune when it did this run process. So the first thing we can ask is how long did it take? We can grab the stats object and then ask for the timestamp when it basically ended and the original timestamp. And we can see it took about almost 6 minutes. Someone asked, is this Jupyter or another notebook engine? It looks like while execution of a cell is in progress, the following cells don't run, they get queued up. Yeah, that's exactly right. We're just using the I think what we're actually running is, this is a conda environment behind the scenes, and it's running Python 3.6, and we're letting Jupyter run with that kernel. And yes, it is one cell at a time. That's usually what you want. Obviously, the cells here that you're looking at, I wouldn't be able to use until the process finished. There's certainly other times when I'd like to be able to run stuff concurrently, and that's a little bit more work. So let me just respond to these. It's done. There we go. Okay. So again, almost 6 minutes. It'll be a little faster on a laptop. And now we can say, all right, which one was the best? Which one maximized that mean reward? And actually, just so you know, I didn't really say this, but for every tick of the clock that you stay balanced, you get a point. So 500 is the longest before the environment just says that's good enough. And we said, let's try to get up to 400 as the mean for this reward. And sure enough, the smallest network actually gave us that reward. So that looks pretty good. But maybe we should look at all of them just to make sure that there aren't other things we should consider. So if we do that, we can just grab the whole data frame, and Jupyter does a nice table layout for this pandas data frame. There's a lot of information here. I would encourage you to kind of paw through this and see if you can make sense of it. But what we'll do actually is project out a few of the columns that are most interesting, and then we'll sort by the time steps that it took, and that's what this is doing. And then we'll maybe consider the trade-offs that we've had to make here. Okay, so now we can see that the configurations, like I said, there were 4 combinations. All of them scored about the same. Whether you might decide, 400.6 is good enough compared to 415.7, as far as I'm concerned. Maybe that's not the right criteria for deciding the best of these choices. Maybe I actually like the fact that this first one, the 2040 combination, actually seemed to go the fastest. Again, if I want to take this set of hyperparameters, this neural network size, and then train over and over and over again, I might care a lot about minimizing my compute time. And at least from these results, that indicates that the 2040 combination converged the fastest to good performance, even though the score was actually the lowest of the 4 combinations. So that's one of the things you should consider, that maybe what was reported as the best result isn't necessarily the best result. And there's probably other ways we could gain the metric query to return this if we really wanted to. Now the next thing we can do, though, we can actually look at TensorBoard to see these things plotted if we care about that. The first thing that's useful to know is this get best log dir is actually telling us where on our file system all the information is logged. If you wanted to save it somewhere for other purposes, this is where it is. So again, we trained with PPO, Proximal Policy Optimization. We did Cartpole version 1, and here's the hidden network. Again, it said that the 2020 network sizes were the best. We don't actually care about this path at the moment. I just want to point out where things are disappearing to. In particular, by default, whenever these Ray libraries are writing key stuff like this, like checkpoints, if it's RLib, or things like this, they're going to go in the home directory Ray_results. So that's the key thing to notice here. Okay, now we can actually look at this in TensorBoard. Now, if you were running on your laptop, you would run this next command on your laptop. TensorBoard is actually installed with the conda environment I ask you to set up if you run on a laptop. If you ran this now, it actually wouldn't do you any good because you wouldn't be able to see the UI, but we actually gave you a link to see the TensorBoard UI. So this is what we have. Now, I actually have some old runs here as well. Oh, no, I take that back. I cleaned out the old runs. So what you can see here is that for all of the runs, the performance is roughly the same. There isn't a whole lot of variation between these. Again, the one that we said we cared about is this reward mean. And you can see that roughly how many iterations it took to get to good values. And if I do this, yeah, so this is a better view. I click this little box with the side arrows to make it resize. And you can see that over some 90K iterations that all of these kind of converged roughly to the same performance, which is good. It means we don't have to really spend too much energy finding a reasonable performing model. So I recommend that you look at this thing as we go through other exercises. If I forget to mention it, you can always check have a look at it and see what's going on. You can go over here and if you let's say I said, what did I say, 2040 was a good combination. I think that's shown here. Yeah, so this is the 2020. Let's turn that off. 4020, 2040. That was the best one. So here's what we think is maybe the best compromise of the 4 options. And if you look at all this data, you can see that it seemed to go pretty well. Okay, so TensorBoard is pretty useful for graphically, reviewing result sets. And in case you couldn't get TensorBoard to work for some reason, I actually put in these screenshots. It turns out these screenshots include data from runs with 60 and 80 as intermediate sizes because I did this. There is an exercise here where I encourage you to do it yourself. If you stay online after the session is over today and you want to play with it, you might try these bigger sizes. It turns out actually going up to like 100, 80 to 100 or so is actually going to give you the best results, it turns out. All right, so let's finish this lesson with just a little bit more detail about some of the other things that are useful to know about when you're kind of exploring results. One of them is this idea of a trial object that the analysis object can return. So if we ask for the best trial, we get something, that the two-string method is terribly interesting. But if we look at the stopping criteria, if we forgot what we said, this is what we picked. There's this big table that gives us a lot of metrics analysis. This is some of the output you would see if we had verbosity turned up. But you could really dive into a lot of information here if you wanted. And actually, this is a repeat of what we saw earlier, that we can also ask it for, how long did it take to run. And then there's a little bit of information about the environment that was used to actually run things, if we're interested in, like where checkpoints were written and stuff like that. All right, like I said, this exercise is kind of interesting to do, but it'll take about 25 minutes. So what you might do is, when we take a break in a little bit, you might just go back and run this. All the code is there. There is a solutions folder here, and this is the notebook that this link points to. And it's all set up. You could just run this and you could then see how it does. And it turns out that the larger network sizes are actually the best choice, more than like 2040 and 4040. So you might try that. Actually, you could run it now if you want, although it will kind of consume the limited resources on this image. So it's probably not a good idea to run it at the moment. But when we take a break, you might just try this and see how it works for you. I'll go ahead and close this for now. Save it so it doesn't complain. Okay, so once again, another question here. What about getting custom information for the execution? For example, given a function to measure the average entropy of each trial, I'm thinking of something like A2C with entropy. Yeah, so there is a lot of other information you can pull out. The particular metrics that are available with this one are the ones that fit cartpole best. What I would encourage you to do is go through the ROLib documentation for like AC2 and see what metrics it exposes. And I think, I don't know off the top of my head, but I'm pretty sure that you can easily grab entropy as a metric that you train against, that you watch as it's training and so forth. So that should work fine. Okay. All right, so that's the end of the first lesson. Let's go back to the Ray Tune folder. And now we'll go into this next example, which will peel the onion a little bit more on Tune, but also explore another level of sophistication in the problem that we want to solve. So what we're going to do now is actually train a PyTorch model. And we'll use the famous data set NNIST of handwritten digits, which is one of the, as you may know, was one of the first really big successes for practical reinforcement, or practical neural networks. So we'll do a bunch of imports, a lot of Torch stuff. If you know anything about Torch, then some of these terms will make sense to you. We won't spend a lot of time explaining it, but I just wanted to use a more reasonable example. This is actually adapted from the example in this link, which is actually part of the PyTorch example set. So you can take a look at that for more details. We'll define a few variables that we'll need, one of which will be a data directory where we'll actually download the MNIST data to the machine relative to the current directory. And also, there's a file here called mnist.py where I actually have all of this code. I wanted to put it inline here so that we could walk through it and talk about it briefly. But in the solution for this, for an exercise for this notebook, it was just easier to import everything from a file. So for your convenience, you can grab this mnist.py file to get all of the definitions that we're using here. So first, we'll use PyTorch to define a convolutional neural network, with various parameter settings. Then we're going to define a data loader, which will actually do the process of downloading and extracting the data that we need. It also embeds something called a file lock so that it's a little bit safer if you had a larger array cluster or you were running a bunch of things on the same machine and they were all trying to hit the data at the same time. This will help prevent corruption from concurrent access. But otherwise, it's really just like creating the folder we need and then downloading the data sources from these, using these torch utilities that we need for MNIST. So we'll just define that. And then here's the function that will do training for us. We'll train for some epoch size. We'll basically compute the loss, do basically stochastic gradient descent, propagate the deltas backwards, the usual thing you do for training a neural network. We'll also split the data into a training data set and a test data set, and this test function will do the test process for us. And then we'll have this driver function that's going to use get data loaders to fetch the data, create the convolutional neural network we need, and then use SGD, stochastic gradient descent, to actually optimize the model. So it just kind of is the driver for everything. Now, if you were doing this without Ray, with PyTorch, you're doing this without Tune in Ray, then you would probably just run single threaded essentially on your laptop. Maybe go to the trouble of setting up distributed training, but it's a non-trivial process. But just to give a sense for how that might look for starters, we'll set up the configuration that provides the different values for the learning rate and the momentum hyperparameters that we want to train for. So here are the values we're going to use. Your momentum is a way of fine-tuning how SGD works, if you're not familiar with the idea. So we'll set that up, and we can see that we have, which you can see visually, we have 12 different combinations. We have 3 options for the learning parameter, 4 for momentum, so we'll try 12 different combinations. And we'll just train it once. We'll do one training round just for grins, and we'll actually do this for real with Tune. So this is our process running for one iteration. And now we'll see how easy it is to do this with Tune. So once again, we'll import Tune. These 3 steps we have to do, including Ray and init, because we're in a new driver program. In Ray terminology, it's a different notebook, it's a different Python process, so we have to do ray.init again. So we basically see output that we saw before. And now when we do, this is Tune's way of saying, I want you to try these combinations of parameters. We're going to do grid search, which is the simplest sort of naive approach of just searching combinations. In the next lesson, we'll talk about smarter ways of traversing the space of possible hyperparameter values. But here we'll say, I want you in this, well, basically I'm going to pass this dictionary to Tune, and we'll say that, yeah, we want you to try these combinations of learning rates and momentums. I think I evaluated this one already. And then we're going to redefine this train MNIST, and really only making one change. We're going to use Tune's report API to report the current mean accuracy that we've achieved as we go through iterations of training this model. The only difference is this last line and also the import statement in train MNIST from the version that we defined up here. That's the only difference. Up here, we just did print. Okay, let's evaluate that. And now we'll actually set up the experiment. Now, it turns out today, we're defining this function train mnist as the thing that will pass to tune to do the running. If you may recall from, this is the RLU one. Let me close that. When we did training up here, let me go back to that. This first argument we passed to tune was actually a name of PPO, and Tune knows how to associate that with the implementation in RLib. What we're doing now is we have a function that's going to do the training, and that's the thing we're going to pass to Tune in this cell. You can also define a class to do this as well. I'll show you that in a second, but I do want to mention one thing, that they're slowly deprecating the class API. Right now, we do need it for a couple of things I'll show you in a minute. But within a few releases of Ray, you'll just use the functional API, where you define a functional function and pass that and don't use the class API, just so you know what's coming. But right now, Ray 086, which is the version we have today, you'll have to use it. Use both. All right, this time we'll stop after 20 iterations. We're using that config object that we defined up here. Now, we could add other configuration values here that don't actually need to be tuned. Like, I don't know, let's say we had, maybe we had like a, like a decay parameter that we just wanted to fix and didn't want to train. You can just put in parameters that you don't need training, and they'll just be used the same value all the time. But that's what's going on in this, where it was in this config object. And then we're passing our stopping criteria of train for 20 iterations. This runs reasonably fast. We'll run this again. You can see that it's running about 12 combinations, and here it's printing out the different combinations of the learning parameter and the momentum. And it's also doing some downloads as we go. I think this is the data set for MNIST. I think by default, the verbosity is set to 2, so you can see this is printing out a lot of stuff. It's kind of useful to see this a couple of times and look at it, but after a while, you'll probably use 1, or if you just don't want to see anything, you can use 0 for the verbosity. And again, that was verbose equals number. And it's nearly done. Actually, it might be done. Yeah, it's finished. If you're new to notebooks, these little square brackets show a star when the cell is running, but when it finishes, it will show the number in sequence. So this is cell 15 that we evaluated, or code 15. We're done. And now we can ask the questions that we asked before. What's the best combination? This is what it says, gave us the best results, which is mean accuracy. Again, accuracy being what's the difference between optimal results and the error that we get. We can lay out this table again. Here I just took the head or the first 5 or so elements. If I dropped head, let me just get rid of this. It would put all of them. So this is the whole data set, which is fine. It's not that much. And now if we actually look at just a subset of it, once again, the mean accuracy is not that different for the first 5 or so combinations of learning rate and momentum. And so that really says that maybe we shouldn't worry so much about as long as we stay within this set of this combination, then maybe we could think once again about how long did it take each of these to run. Now, unfortunately, because for speed reasons to have this run quickly, I had it stop after 10 iterations. So there's really no information here about how long it would really take to get good results. But what you would really do if you wanted to do this for real is let it run for a much longer period of time, and then evaluate the trade-off between the performance time, how long it took to do that training run, and the accuracy that you get. But for these combinations, they look pretty good. Whereas down here, it's not so great. And the reason it's not so great probably is, if you have a really small learning rate and a really small momentum value, really small momentum value is like having no momentum, which means that you're back to the case where you don't use momentum to help speed things up. And a small learning rate means that you just converge very slowly to the answer. The advantage of a smaller learning rate is that you don't have a tendency to overshoot and hop back and forth around the optimal value. If you're converging slowly, you're more likely to converge to the true best value, but you'll just take longer to get there. So that's sort of the trade-off you make. And this only took less than a minute because we just had everything finished fairly quickly. But here's another thing you might consider. You could do experiments where you say, you know what, in my experience for this problem I've been working on for a long time, if I do these quick runs, that truncate after some small number of iterations, that gets me down to a smaller configuration set that is probably going to be optimal. And then I can just focus on those rather than doing long training runs with values that are suboptimal. I can kind of triangulate to a good subset quickly. We'll also look at a tool shortly for doing this in a more programmatic way, where instead of you sort of manually doing it, it tries to adjust the values to find an optimal set for you. All right, let's look at this with the class version. So I've defined a class that basically is going to do the same sort of stuff that I was doing in the function version. And I think there's something else it's doing here. I think this also has a hook for doing checkpointing. Notice that we're subclassing a tune class called trainable. We have to define a setup that initializes everything, and then the training process is defined with this method. So these are the two minimal set of methods you have to define. And now if we run the same exercise with this, we'll get comparable results, but because we're truncating early, there'll be some stochasticity, so the actual tables might look a little different, even though nominally they're doing the same thing. But this should take roughly about the same amount of time. Someone asked a question, is it possible to run nested search, as he put it? And that is, like, maybe find the best possible convolutional network architecture from a fixed set, each having a different number of hyperparameters, or do you have to run these sequentially? I think the answer to that is, and I'm not really a tune expert, to be honest, but I believe that some of the stuff that we'll see in the search algorithms gives you more flexibility in doing this kind of sort of intelligent triangulation to the right answer. So I hope that'll answer your question. If not, one thing I'll mention offhand is, if you go back to the overview top level notebook, there's information on joining the Ray Slack, and there's a tune channel in the Ray Slack that's really a great place to ask these kind of questions, where the idiot instructor doesn't necessarily know the answer. So. All right, this finished. It probably took about the same amount of time. We got a slightly different answer this time. I believe it was, what was it up here? It was actually 0.1 for the learning rate and 0.9 for the momentum. Once again, it's probably just that the values are so close that it's sort of an arbitrary, oops, wrong thing. It's kind of arbitrary that it's different. If we look for the, compare with some of the others and then do this one in particular, once again, the numbers are pretty close up here. And so it's really hard to make a choice. Just on the way we've done this setup, it's hard to make a choice for the best combination. And just for grins, how long did that take? This was a little bit longer, 30 seconds, 35 seconds. Okay. Yeah, someone also mentioned that data loader should only read the file, something that is safe as long as the workers don't share the same file descriptors, so they don't mess with the file pointer like fseek and so forth. If Ray spawns executors or executions of the data loader after forking or threading, then each one should own its own file descriptor and read-only access to the file system. Yeah, in other words, I think you're right. Just to paraphrase that, I'm not actually sure that the logic that we had in the data loader is entirely necessary because when you're actually running in like Ray in parallel, each of these workers is actually a separate Python process. So it's not possible for a separate process to share file descriptors to talk to the underlying file system. So it probably is safe if things are at least reading at the same time. I think the concern with that code is trying to address is the risk that you have, you try to sequentially write to the file, but like two download processes happen at the same time, and they're both trying to write to the file. I think that's actually the problem that it's trying to address. Okay, we'll go through the last lesson, which is the search algorithms and schedulers, and then we'll take a break, and then we'll finish the day with Ray Serve. So let's do that here. So this is, actually, we'll have a fourth one. We'll take a break, and then I'll do the Ray SGD lesson, but we'll do this as the last notebook before we break. Okay, what's the idea with search algorithms and schedulers? Well, as I mentioned in the setup, if you're doing neural architecture search, there's an insanely large number of possible combinations you could pick. Another way to put it is the feature space is enormous. So you need some intelligence to try to hopefully limit what you're searching. And one way to do that is to prune combinations of hyperparameters that seem to be performing poorly, or to notice which ones are performing well. And if you try variations on those rather than naively trying everything, then hopefully you'll be better. In other words, think about grid search. If I naively try all combinations, I'm completely forgetting everything I've already observed by previous combinations. So maybe I could use a way of leveraging what I already know, and that's sort of where Bayesian optimization comes into play. These combinations seem to work well, so that should sort of favor my search for new combinations. And also, if I pick a combination and it seems to be performing poorly relative to how others performed during the training iterations, maybe I should truncate that, just throw that combination away and go on, so that I basically abort something that's not going to perform well. And that is really kind of the essence of what some of these search algorithms are doing in schedulers. So the schedulers, just to go to that first, would be things like this median stopping rule is a simple example. If I see that this combination is underperforming the average or the mean, or the median rather, of all of the other combinations I've tried, then chances are good it's not going to get any better. I might as well just stop and go on to another combination, so I don't waste energy more than necessary pursuing that one. Hyperband is doing a stochastic exploration, and it's actually leveraging the multi-arm bandit concept so that it's learning as it goes what combinations seem to be working best, with some awareness that it has to be able to explore other combinations. If you know anything about reinforcement learning, this is one of the big questions in reinforcement learning algorithms is, I could try this, and this seems to be working well for me, but until I explore something else, I may actually discover that there's actually a better thing I could be doing. So it's exploration of this space versus exploitation becomes a pretty important concept. And that's what the schedulers are helping you do, is to truncate explorations that appear not to be working well and to focus on things that are doing a better job. So I put in a list of and links to some of the algorithms that are integrated into Tune for both search and scheduling. And I say integrated because most of these are actually third-party libraries. Like the example we'll use is this HP Banster that Tune integrates nicely. And there's a more complete list if you look at the documentation, but I just picked a few examples here to describe. For time's sake, I won't go into more detail, but we'll actually do an example of one of them. And the one that we'll do actually combines a search algorithm with a scheduler. And that's one of the decisions you make is, do you just use one or the other, or do you combine them? So let's go ahead and, actually we can skip this. We already know Ray's running. We'll initialize it as before. And what we're going to do is Bayesian optimization hyperband, which is combining this idea of building an awareness, sort of a belief network about how well this is going, but also using a multi-arm bandit to kind of model what's going on with the system. We have to do an install, which is what this pip install does. And also, the other thing that Tune handles nicely is this library has its own way of being configured. It's this config space module. And that's what we're going to actually do or use to configure the scheduler. And this takes a moment to download and build and whatever else it's doing. And we'll combine that with the scheduler that's built for it, which is Hyperband for BOHB. And of course, these links go to the documentation in Ray under the Tune section. And that's still running. So I'm going to go ahead and evaluate the next cells. You can do that too. As we said earlier, these will just wait until the download is done, but we can start talking about what they're doing. So we've done some imports. We're going to use MNIST again. This is that class that I defined in the previous notebook, but it's in this mnist.py file. All right, so we're going to do the same training that we did before with the learning rate and momentum, and this is how you set up this config space to do that. And I guess we're done. You can see that I'm now getting these cells evaluated. We'll define this dictionary for the metric that we'll track, which is mean accuracy. And what we're going to do is try to maximize that accuracy. And we're defining a dictionary because we're going to use it twice. Once when we set up the search algorithm, which again is how we search the space of parameters. And then one which schedules them and handles things like, premature, or not premature, but terminating a bad performing trial and that sort of thing. So we'll evaluate this. Oh, don't you love it when it fails? Let's see. Oh, okay, right. Sorry, I forgot about this. It turns out this is not going to work today, and I didn't set this up in advance. Give me a chance to set this up quickly on my laptop. The reason it's not working is that we're actually running a relatively old instance. Oh, I see what it did. Sorry. I'm typing into my terminal off screen here. This sets up a Python 3 environment in a relatively old Amazon AMI, and unfortunately, there's some library conflicts that cause this exception. So what I'm going to do is show you this on my laptop. Yeah, these are already downloaded, so we can go ahead and import, define our configuration. This should work now, he said. Yeah, it did. Good. So we set up our search algorithm, our scheduler, and now we're going to do training. Notice there's a max time steps here. That's going to make it run reasonably fast, so we won't spend too much time. Also, my laptop has 8 cores instead of 4, so this will be able to run things with more parallelism, and we should be done pretty quickly. I'll go ahead and evaluate these so we can have a look at the results when they finish. What we'll actually find, I think, if I remember correctly, is that it'll actually take longer to run with these algorithms than our more naive approach that we used a minute ago. That's okay, because we're actually solving a simple problem. Where these sophisticated algorithms and the overhead they impose are going to prove valuable is when you're doing something that's much bigger, much more sophisticated, much broader search space than what we have available to us here. So, it's okay for us to, take more time for this algorithm, but when you do you have a real problem to solve, then you'll want to use something like these search algorithms. Let me set up this exercise. What I'll ask you to do, this takes a little while to run too, and I'll ask you to go ahead and run this because we're going to take a break in just a minute. While it's running, you can just run this. Population-based training is a really cool idea. It's the idea that the system will watch how these different combinations of hyperparameters are working, and when it sees a successful group running, it will actually tweak the values and try a new trial with those permuted parameters or whatever, so that it tries to converge to an optimal setting. You can see this took a little over a minute, the one that we just ran, whereas previously it was on the order of 40 seconds or something. And it reports what it thinks are the best values, and we can, otherwise we got similar results to what we saw previously. So we'll take a break. I have 9 minutes after the hour. Let's take 15 minutes and come back at 25 minutes after the hour. And I encourage you to go ahead and run this. I think everything is set up to run. If not, if for some reason it doesn't work, just go into the solution notebook. Again, RayTune Solutions #3 and run it there. And you can see how this works. But this one takes a while to run. Okay, see you in about 15 minutes. Okay, let's start again. I'll just briefly talk about what this population-based training exercise is doing. Once again, most of what's happening is the same as what we saw, the same sort of finding the right learning rate and momentum. This perturbation interval is like after every n time steps, and I picked 10, which is maybe a bit aggressive, but because we're not training for a long time, it will kind of tweak the parameters to try to find something that works a little better. And then the stopping criteria, either we achieve a mean accuracy of like 97% basically, or we train for 600 steps and then stop. I found the 600 was useful when I was experimenting with this because some of these would just keep going forever for bad criteria if it didn't have something as a stopgap. And when we do that, we find that, it basically decides that 0.1 and 0.1 are actually the optimal values for these two. Now, these cells that I'm looking at, this is actually in the solution folder. I forgot to mention there is a solutions notebook. One of the things that's not in the original notebook is, which was kind of left as an exercise for you, is to take the same analysis cells that we had been using before and try them yourself to see how it goes. And you can see that from this last table that, that choice of 0.1 and 0.1 is actually pretty good in terms of the number of training iterations required to get to that point. Whereas it looks like 0.01 is the learning rate and 0.1 is the momentum. That basically hit 600 and then it just gave up. So, 10 times more training runs there and never got to the criteria we wanted at 0.97. So kind of a cool tool for, exploring the search space and, fine tuning the results as you go. And this took about, 3 minutes to run. All right, I'll go back to the other notebook environment. We'll go through the last lesson, which is fairly quick. This is about Ray SGD, and then we'll switch over to Ray Serve. So if we open this notebook, so what Ray SGD is designed to do is to make it easy for you to scale training as opposed to hyperparameter tuning of jobs in PyTorch and also TensorFlow over a cluster, leveraging Ray to eliminate some of the challenges of doing it without Ray. And so it was written with these goals in mind of ease of use primarily, making it easy to compose what you need to do, and then making it easy to change the scaling that you use as you proceed in your work. So I'm adapting an example that comes right out of the Ray SGD documentation, and really just to give you a flavor for how it works. Once again, we can skip this step because we know Ray's running. There's some imports. Notice that we have a couple of new ones from within Ray itself. Technically, this library is not part of RayTune, but it's written by the same team, and it sort of is simpatico with the goals of RayTune as well. Now we'll start Ray again in this notebook, and we'll define a bunch of functions that do some of the work we need to do, like creating a simple model, an optimizer for improving it with stochastic gradient descent, and then a simple data loader to pull in the data that we need. And then we'll define this torch trainer object. This is something that's built into the library that was imported up here out of the SGD library. And there's a bunch of parameters you pass, like these functions we just defined, whether or not we have a GPU. We'll just use a built-in, mean square error loss function. And then we'll do a batch size of 64, which is 64 records at a time. We want to do a full training process. We'll just run, with 10 steps, and this is basically what you get. So it's pretty easy to wire this together. Again, behind the scenes, it's going to use Ray. So if you have a really big training problem, it can do distributed training for you. Fairly new library, and they're looking for feedback on how you like it, and I encourage you to check it out. So that was just a quick introduction then to Ray SGD. And we're down to about 30 minutes left. What I'd like to do then is spend the rest of our time on Ray Serve. Ray Serve is a library for model serving. So if I open up this notebook. Oh, before I leave, let's go back to Ray Tune for a second. Once again, please give us your feedback. There's the survey at the bottom of the overview notebook for Ray Tune. Please fill out that survey if you wouldn't mind. And there is another one for Ray Serve here, if you wouldn't mind filling that out as well. They're pretty quick, and I hope you'll find it informative to give us feedback. All right, so we're looking at the overview. Not much here as usual. This is just really a table of contents. Let's go to the first folder, which is discussing the challenges of model serving. That's what Ray Serve was designed to do, is to make it relatively easy to build scalable model serving applications. What we're actually going to see, though, is it's not really limited to model serving per se. It can serve anything that you want to define as a function or a class to process incoming requests, do something with them, and return results. So it's a nice general purpose framework originally built for model serving, and we'll see how it nicely supports some model serving implementation patterns, for example, but it's really quite general purpose and quite flexible. Well, there's a lot of challenges. I did not mean to go into Markdown there that you're going to need in a typical environment. The first one is, data science. You work in a research environment. You have your ways of building models, but the production deployments can be quite a bit different. So we wanted it to be much easier to do this, especially if you, as a data scientist, are wearing a lot of hats, including the person who owns the production deployments. First of all, it needs to support any framework you might happen to be using, like PyTorch, TensorFlow, or whatever. And as I mentioned, we'll just define some arbitrary functions that have nothing to do with those frameworks, and we'll serve those as well. If you're a data science environment, you're probably pure Python. So it's a nice way to be able to deploy models without having to run JVMs, which is commonly done. It's simple and scalable to use, as we'll see. Because it's a programmatic API, you can embed it in your applications how you see fit, although the way we're going to use it is as like a RESTful server. And that means, though, that if it's embeddable like that, then you can integrate it and script it or whatever to integrate into your DevOps deployment environment. So that, like if you have a pipeline for training and then testing and then deploying models, you can integrate this with that as you see fit. And we'll also look at some of the deployment patterns you might want to implement, like the canary deployment pattern. We'll see what that is shortly. Ray Serve tries to satisfy all of those requirements. I won't belabor the point here. Well, let's just see an example. We'll start with two simple ones. Once again, I'll skip the shell script. So we'll import Ray and import Serve from Ray, and also import this third-party library you may have used before for requests. And that's how we'll actually send HTTP requests to this running server that we're about to start to do serving. Now, what you typically will want to do is initialize Ray first, the way that you want to initialize it. In our case, we have Ray already running. We're doing this address equals auto, which says find the running Ray cluster. And then we're going to initialize Serve itself. What this actually does is it's starting some background processes. It's actually using a so-called named actor that has the name serve example 1, because that's what I used. The concept of named actors is covered in our Ray crash course, if you're not familiar with that. It's really an implementation detail. You don't really need to know what it's all about. In a lot of ways, though, serve kind of looks or feels familiar if you've used Flask before to stand up like web services or whatever. So for example, when you define a function that you're going to serve, it needs to accept a Flask request object, and that's how the information will come in through HTTP. So in this case, all we're going to do is return a string that includes the name argument that you pass on the in the URL parameter list, and then if you don't actually provide that parameter, or if for whatever reason it's not there, then we'll just return serve exclamation point. So that's our function that we're going to serve. This could be a TensorFlow model, something like that, but to focus on the concepts of serve and not other things, we'll see that in a second. But for now, will just serve this function. So the first thing you do, and actually I've combined them into two steps here. Let me just split this actually. So I'm going to do a fancy trick here. This is Control-Shift minus sign that splits cells. I'll create a backend first. And what this is doing is I'm passing this function to the serve system. And I'm saying I want you to create a backend that will handle requests and give it this handle hello. This needs to be a unique string, okay? And then we create an endpoint, which is where you define the route. So when someone does, our HTTP request /hello, it will go through this endpoint to this backend that was, indicated by this hello identifier. And now we can try it. So we'll use that request library. We'll do a get request, which is by default what we've defined only for this endpoint, that it only handles HTTP gets. And here's what the URL will look like. This thing is actually running on port 8000 rather, and the route point is hello, and then here we're passing the name argument. In this case, we'll pass request _ integer for this count that we're doing. So let's try this and see what we get. And as you would expect, it just returns hello request _ number. So pretty basic. All right. Well, suppose we wanted to keep state though, like, for example, how many times this has been called. So let's use a simple example of a stateful object that we want to serve, and that will be some counter. Every time we call it, it's going to increment some internal count and then return that value. And notice what I did here. I'm actually returning a dictionary. You don't return a Flask response object, which sort of what you might think since you're taking in a request. You just return a dictionary, and then it gets processed into the right objects behind the scenes. So I'll return the current counter, and then I'll return whatever arguments you pass to me. So once again, we do sort of a similar thing. We'll create a new backend with a new name called counter. We'll pass the name of the class. And here's the advantage of using classes versus methods. We can also pass constructor arguments. In this case, the initial value for our count, which also defaults to 0, but we could also pass a value here. So that's the one advantage of using a class and not just a function. So we'll create that, and then we'll create a new endpoint for this using that same backend and using the route /counter. And now if we call it, what we can see is that we passed in a value I, although we're actually ignoring it. We're not using it at all. But we returned that argument that we passed in as well as the current count. I should probably change this to be something different than I equals because it's a little confusing. Maybe put in back the name equals thing I used before. But anyway, I'm just dumping the arguments that you passed as part of the parameter list here, and the counter, whatever the current value is. So it's a nice stateful service. And you can imagine, obviously these are trivial examples, but you can imagine layering something much more sophisticated behind the scenes for model serving or something else that goes through these simple abstractions. Okay, well, let's build on this a little bit. Suppose we want to add a new backend and maybe a new endpoint. And let's talk a little bit about this concept of backends and endpoints a bit. They're defined in more detail in this link, this section called Key Concepts in the docs. But basically what Serve is trying to do is make a nice logical separation between the backend logic that shouldn't have to know anything about HTTP other than the Flask object, I guess, the request object. And then how we actually wire those backends together and expose them to the outside. So the router or the request or the endpoint, sorry, the endpoint concept is where we make that association with external URLs, the API, as it were, the RESTful API, and then backends are where we embed the logic for doing work. And that's really kind of the gist of it. Now we can create more of these. We can create backends all day if we want and not actually associate them with an endpoint. And what I'm going to do here is actually just create a dummy backend called counter and create a new instance of it. I could actually have passed, if I was using the function API, I could pass in the same function. That would be okay. But what's useful is we have this list backends method. So if you forget what you've defined, this kind of gives you the complete list of everything. And you can even delete them when you're done with them if you're like doing an experimental deployment. If we do this list again, then we're back to the original 2 that we had. Notice also it's showing us stuff like whether we've configured a maximum batch size. That's one way to do things. This is a hook that we don't really get into in this lesson, but you can also set up batching. Like if it happened, like let's say you're calling an expensive neural network behind the scenes, and it's much more efficient if you send like 100 at a time rather than 1 at a time. You can configure batching and do it that way if you prefer. And also if we need if we have a lot of traffic, we can increase the number of replicas to handle the load. So that's what these are showing us. Right now, we're just using the default settings. So then, in contrast, endpoints are where we define the HTTP methods that we want to provide access for and the route that will define them. And what I'm going to do here is use the same hello backend function that I used before, but now actually support an endpoint so that you can send a post request to it. And now if I list those points, you can see here I just pulled out the keys for this list of endpoints. I have 3 now: hello, counter, and post hello for post request. And then here are the details for each of them. And now if I try using this, where now I'm just calling post hello, and now notice I'm doing a post request, and here's how I pass data. This is basically form data, which is the canonical way that you use posts. I'm trying to do the same thing I did before with the original hello implementation. But you may recall that this was the default if it couldn't find a value for the argument of with the key name. So my original implementation of hello isn't very flexible for doing post requests because there actually is it doesn't know how to get form data out of the request when it's a post request. It really only understands GET requests. So why don't we fix that? And one way we could do this, and this is going back a little bit to the patterns of model serving, we could say, well, I'm going to implement a better version of my model, but I'm paranoid. I don't really know if it's actually better. For sure, when it's faced with real traffic, I think it's better. So what I want to do is actually route just a tiny fraction of my traffic through that model, while most of the traffic is going through the old model. Like a canary deployment is the term of art. And then once I'm convinced that the performance is as good or better than the old model, then I can reroute all traffic to the new model. So that's sort of the idea with canary deployment. There are similar kind of partitioning patterns like A/B testing if you have 2 different websites and you want to see which one seems to work better, that sort of thing. But we'll do kind of the canary deployment. And what we're going to do is implement a new function called new echo that now will first ask if there's an argument with the key of name. This is the original implementation, and return none if it doesn't find one. And what that will mean is if none is returned, it will do this second clause, which will ask if there's a form data element called name. And if that doesn't return anything, then we'll fall back to using serve exclamation mark. So whatever we get for this name, we'll return that. And I also appended this little string new here so that when we run this with both versions of these backends running, we'll be able to see which one processed the traffic. So let's define that. We'll create a new backend called new hello. And now we're going to create a new endpoint. And we'll start off by, we'll call this canary endpoint. And we'll start off by having it just go to the old backend with the route path of canary test. And we'll support both get and post. Okay. Now let's change the traffic routing for this endpoint. So for canary endpoint, we're going to set a traffic routing where 75% of the traffic goes to the original hello, 25% goes to the new one. Now this isn't quite, I mentioned a canary deployment, it would be more like maybe 99% and 1%, but I did 75, 25, so we definitely see both of them being used in the output without having to run a lot of queries. So now if we try that, and let me explain what's going on here. Notice where new appears. So we had 4 cases where either 2 GET requests and 3 post requests were processed with this new handler. Notice that for either the old handler or the old backend or the new one, we got the same behavior that we wanted. It always found the request object and returned it. For the but once again, if we use the old echo method for post requests, we don't find the name value. But if we use our new implementation, now it actually finds it in the form data, as we said. So that's what we like. This is actually working properly. It handles both GET requests as well as POST requests. So that's the one we want to use. So what we would do now is set the traffic once again to just send it all to the new hello backend, 1.0 or 100%. Obviously, these numbers have to add up to 1.0. Otherwise, you'll won't be happy. So now if we do this again, and we can see that we sent all traffic to the new implementation, and all of them properly handled this name value, whether it was treated as a form field or as a parameter in the URL. Okay, so that's the idea of one of the patterns in model serving that's actually a general pattern for application development, where I do a trial deployment, I route some traffic to it dynamically. When I'm satisfied, or maybe I reject it, whatever, then I can route all the traffic to it or throw it away and route to the next one. I can dynamically, while things are running, define and delete backends. I can add and remove endpoints, and I can change how traffic is routed between them, all dynamically in this running application. Now, this last section talks a little bit about the way serve is implemented. This is probably going to change a little bit, but right now it's basically a singleton running in the whole cluster. I did give it a name at the beginning. When I said serve.init, I gave it a name. It's not quite finished, but there will be API calls where I can delete those named instances without affecting others. And we may even do other changes to the API. But at the moment, it kind of runs as a singleton across your entire cluster. You kind of need to be aware of this because it does impact how, like when I go to the next notebook, we would actually see those same things visible to us because we're sharing a Ray cluster across all notebooks. But one of the ways you could clean up if you wanted to is just get all the endpoints and delete them. You get all the backends and delete them. And then if we list what's left, we'll see that we've gotten rid of all of them. Although that core Ray serve actor that we defined way up here, where was it? Oh, it's all the way at the top. Here it is. Serve.init name serve example one. This is actually still running. I do have a comment at the bottom that the next release of Ray will have a serve shutdown method where you can get rid of everything. But right now that isn't in the system. Okay, there's no exercise for this one. One thing I wanted to mention, actually, that I did this, actually I didn't do it like I thought. I clicked this second tab over here, and if you're starting to get warnings about, oh, you've scheduled a bunch of Python processes and nothing's available at the moment, you could go in here and shut down the notebooks, actually the Python interpreters behind the scenes, for the ones that we don't really need anymore. Like we don't really need the overview. Let's leave the Ray serve one up, but we can get rid of these tuned ones, SGD, and so forth. So that'll clean up a little bit if you find you're getting warnings about stuff is running that is kind of annoying. Okay, the last notebook we'll go through today is a slightly more evolved example that's actually doing real model serving. Let me go ahead and import a few things here. Basically what we did before, start Ray locally. Now here's an example of where the existing serve instance is affecting us. I actually have to use a new port. So you can specify a particular port that serve will work on, and we'll use 8001. Here's those messages I mentioned. There's a lot of stuff running. Hang on just a second. Let me get rid of this. Just give me 1 second, sorry. The building just tried to call me. So you can see the warnings I was talking about. These are small instances. Cleaning up helps get rid of some of this, but you can kind of ignore them for the most part because things will get freed up as we go. All right, so what we'll do actually is we'll use an example from scikit-learn, and we'll train something using gradient boosting classifier. We'll actually use that iris data set that I mentioned briefly when I cited the example of k-means at the very beginning today. So we'll load this data. We'll have both a test data set and a training data set. We're using facilities and scikit-learn for this purpose. Create a gradient boosting classifier. We'll randomly shuffle. This is a typical trick, when you split the data to randomly shuffle it. And now we'll train a model with this. And it happens pretty quickly. It's a fairly simple data set. And then we're going to go ahead and write these model parameters to the local file system. This could be to S3 or some other global place. It's kind of arbitrary where you put it. The only thing I'll say is that when we get down into model serving, this does need to be a fully qualified path. It can't be a relative path because these processes will not necessarily have the same current working directory. So that's why I'm using an absolute path for writing this pickled model file and then this JSON file. So now we can create a class that wraps this. We'll call it boosting model v1. Notice when it initializes, it'll open up those files we just defined and load the model and the list of labels. And then there's this call method that will be invoked to actually do scoring in real time. And what we'll do is, we're telling it things like, we're going to get this input data that will include various measurements of orchids, or irises rather. And then we're going to actually ask you to predict which species of iris this actually is. That's the idea here. Once again, like before, we create a backend and an endpoint, and we're calling this v1 because we're actually going to deploy a second one shortly. We'll do a request with the given data, and the result that it returns is this is a species called Setosa, is what it thinks corresponds to this particular set of data for the request. Now, what if we want to update the model? Something that's more real world. We typically realize that models drift over time, and we need to redeploy. Sorry, somebody posted a comment to me here. Something about some guy named Jan from Facebook, Y-A-N-N, joining in. I don't know what they're talking about, but anyway. All right, let's train a new model. It's kind of going to be very similar to the old model, but we're going to go through the same steps. Now, this is the point where you could imagine you've got some automation running. Maybe you're measuring metrics of performance, and every now and then it's going to tell you that you're regressing, or the model is getting worse in terms of its performance. So you retrain and then redeploy. We'll define a new class to wrap this. This is not necessary. This is a convenience. Really, the only things that are different here are the particular files that we're loading. So one of the little exercises that I would encourage you to do on your own time, we won't have time to do it today, is to just get rid of the duplication and have one class that you use instead for this. But anyway, so we'll have this model, or this class that encapsulates the second version of the model. We'll create a new backend for it. So we have both of them running now. And then we'll route some of the traffic to the new one, some to the old one, like we did in the last lesson. And now if we do a request, there's a bit of background logging information that's kind of in the way. Apologies for that. But you can see that in this case, we actually got all of them went to the same one. So let's run that cell again. That's very interesting. Okay, now we actually got 2 out of the 10 that went to the new one. And it actually made a different prediction, Virginica instead of Setosa as the prediction. So once again, just a little bit more real world, actually using real models. In particular, what we're seeing here that we haven't seen before is what do you do about model artifacts? Typically the way you do it, store them somewhere central, globally visible is required. Define a class that encapsulates where they are and how to load them, how to work with them, how to do scoring with them. And then create a backend for that class, and then define traffic and endpoints in the usual way. So what you could do is if you want to play around with this for a while longer, we're going to wrap up here in just a few minutes, is You could try cleaning up the duplication in the model versions, try some new models, try changing the traffic patterns. Think about how you would automate this, how you would turn everything like in particular cells like this into a method, and maybe write a loop that, for every, minute or something, trains a new model, deploys it, gets rid of maybe the oldest model, kind of, it works through like basically a queue of models or something. You could play with that idea to see how this might fit your needs. And when you're done, you can evaluate this cell if you want to. It's not really necessary because we are actually done for the day. What I'll do before I take any final questions is to remind you to go to the survey at the bottom of each of these overview pages. If you don't want to do two, pick one that's most interesting to you or you feel most passionate about, whatever. And that'll give us some nice feedback about how you liked it. But we actually finished 5 minutes ahead of time. I'd be very happy to take any questions anybody has or any comments or whatever, and then we'll wrap up in a few minutes. So I don't see any open questions at the moment. Let me go back to the, while I'm waiting, let me go back to this first tune notebook. Another thing you might do is, where is it? You might try this exercise too. The easiest way to do this, if you don't want to just modify the code, is go into the solutions and just run this notebook, the first one that actually sets up these parameters and runs it. See what kind of results you get. Also, I should say, since you have this environment you can play with, if you're interested in any of the other courses that we've taught, you could just navigate to them. You could look at the Ray crash course if you're fuzzy on core concepts of Ray. You could go into the advanced Ray if you know a little bit more. I really enjoyed teaching the RLib stuff. This is by far the biggest tutorial. There's a lot to cover here. You're welcome to play with that. Once again, we remind you to register for Ray Summit. That's coming up in end of September. Either go to raysummit.org or the Anyscale.com events page to see more information. Sign up for our next Ray Summit event. Actually, the creator of Serve is speaking at this one, Simon Moe. He's going to talk a little bit more about Serve and where we're going with it. And I do appreciate your attending and encourage you to fill out the surveys, anything else you want to provide in the way of feedback. I do have a question now I'll go ahead and take. What is serving inference in this example? TensorFlow serving something else. So I assume you're referring to the example we just looked at with scikit-learn. What it's actually doing is we gave it a model, and let me just go back to it here. That was here. So we gave it this model, this object, and it has these defined methods like a regular constructor, but also this call method. And so it's going to simply, as requests come in, these requests will be packaged as Flash requests, and it will send them in here. And then as far as Serve is concerned, it has no idea what's going on at this point. In this case, we're actually using the scikit-learn model to do scoring. This could just as easily be a TensorFlow model that you're scoring with, or PyTorch or whatever. So there's actually very little that's built in to Serve right here. You could, if you were doing RLib, like you were doing rollouts or something, you could also embed that in this thing to serve rollouts externally or in some controlled way. Serve is pretty lightweight. It's pretty agnostic about what's going on, which means that you're responsible for embedding whatever logic is required to set up your model serving for your case and to actually do it. But if you already know PyTorch or whatever, then you just use those APIs here and just let Serve handle the kind of traffic routing, the scalability with Ray behind the scenes, and so forth. Yeah, so in general, sort of a general theme about Ray is that we try not to invent stuff people have already done. Like, you'll never see us write our own neural network library because, why would you try to tackle these mature systems? But we can innovate in specific ways, like integrating neural networks with reinforcement learning. That is one area where we've actually written a full library. integrate these libraries with Tune so that you could get hyperparameter tuning relatively easily and scalably and so forth. So that's sort of the model that we followed there. Okay, any other final questions before we stop for today? Okay, thanks a lot. I'm looking forward to seeing all of you at Ray Summit, hopefully, and or maybe at the next Connect event in August as well. Have a good day.